Can you see the screen? Okay. Can you see the equations? Are you able to see?
Yes, sir.
Okay. So these are the equations for what do you say?
Dynamic braking under primary
Transient conditions during dynamic braking or static braking. We have already seen how to obtain dynamic braking in case of a DC shunt motor. Correct? The field winding supply is maintained constant so that the flux remains constant, and the armature winding is disconnected from the supply and connected across a braking resistor. Correct? So I'm not drawing the circuit here. Do I need to draw the circuit? Circuit diagram do I need to draw? Yes or no?
No, sir.
So if you apply KVL in the armature circuit, this is the back EMF, K5 omega, okay? And K5 is taken as the constant small c. So C into omega plus armature current multiplied by the armature circuit resistance, that is equal to 0. Now there is no applied voltage. Okay? Instead of that, we have a braking resistance, and that braking resistance is included in R. This R is equal to the armature circuit resistance plus the braking resistance. Okay, is this equation clear?
Yes, sir.
Yes, sir.
Okay, so if you apply KVL in the armature circuit, this is the back EMF plus IR is equal to 0. I is the armature current, and R includes the armature circuit resistance plus the braking resistance. This is the torque equation. Motor torque K phi I or C into I, that is equal to the dynamic torque component J d omega by dt plus the load torque, that is TL. Okay.
Yes, sir.
Motor torque is equal to dynamic torque J d omega by dt plus the load torque, that is TL. Okay, so if you solve these two equations for omega, instead of I, we substitute this and we solve this. The equation that you get is omega is equal to minus delta omega L plus some constant C e to the power minus T upon TEM. Where TEM is once again the torque constant, time constant, motor time constant that we had seen in the previous class. Now this C is a constant whose value can be found out by using the initial condition. The initial condition is that at t is equal to 0, the speed is equal to the initial speed, omega n. Okay, this omega n. At t is equal to 0, speed is equal to the initial speed. So if you put t is equal to 0, this becomes e to the power 0, that is 1. So C becomes equal to omega n plus delta omega L. Okay? Where this delta omega L is the change in speed from the no load speed under load. That also we have seen is equal to TL into R upon C square. So if you substitute this value of C in this equation, this omega becomes equal to minus delta omega L plus C. C is omega n plus delta omega L into e to the power minus T by TEM. Okay, this is the equation for the motor speed. Now what do we get from this? At t is equal to 0, how much is the motor speed?
Omega in.
No, omega in.
Correct. At t is equal to 0, speed is equal to omega n, that is the initial speed. How much is the initial speed? Is it 0? Is it omega 0?
Sir, 0 or any reference?
Sir, omega 0, sir.
Sir, 0.
It will be omega L. If the motor is running under load, and if it is running at no load, then it is omega 0. Correct?
Yes, sir.
If the motor is running at no load, then the initial speed is omega 0, and if it is running under loaded conditions, then the initial speed is omega L, where omega L will be equal to omega 0 minus delta omega L. And we have to remember that here the initial speed is the speed at which the supply is disconnected and the braking resistance is connected, or it is the speed at which the braking is initiated. Okay? It is not the speed at which the motor is starting. It is the speed at which the motor is starting to brake. Okay?
Yes, sir.
Somebody wants to say something. Okay. Okay. If the motor is running on no load, then this delta omega L is also 0. Correct? If the motor is running on no load, this delta omega L is 0. So your speed equation simply becomes omega is equal to omega 0 e to the power minus t by TEM. Okay, is this clear?
Yes, sir. Yes.
So at t is equal to 0, the speed is either omega 0 if the motor was running on no load, or it is omega L if the motor was running under loaded conditions. And at t is equal to infinity, e to the power minus infinity is 0. Okay? E to the power minus infinity is 0. So at t is equal to infinity, your speed will be equal to minus delta omega L if your motor was running under loaded condition, or it will be 0 if the motor was running on no load. Is this clear?
Yes, sir.
At t is equal to infinity, the value of omega is equal to minus delta omega L if the motor was running under load, and it will be 0 if the motor was running on no load. And how is this change going to happen? There is going to be an exponential decrease. Okay. So on the y-axis, we are going to have the speed omega. Okay, I'm writing W here, but this is actually the speed omega. And on the x-axis, we are having time. So basically, we are plotting speed as a function of time. Now at t is equal to 0, we are initiating the braking. Okay, let us say this is the no load speed omega 0. And let us say the motor was running without any load. So at the instant braking is initiated, this is the value of the speed, and okay, this is the graph of speed with respect to time, and the motor is braked using dynamic braking, okay, without any load. Okay, is this clear? Any questions? Yes?
No, sir.
No, sir.
No, sir.
No means not clear, or no questions?
No question, sir. Clear, sir.
Okay. If the motor was running under loaded conditions, let us say this is delta omega L. Okay, this is delta omega L. So this is your omega L, speed under load. Okay. So initially when the braking is initiated, this will be the initial speed, and the final speed will be this. Okay, how much is this?
Minus delta omega.
This magnitude is delta omega L. Okay, this magnitude is delta omega L. Okay, in practice, your motor speed will not become negative. In fact, the motor will stop at this point. Okay. This point is given as B. Okay. In the book, you read the book, you will see that this point is denoted by small b. Okay. So your motor will stop at this point with, what do you say, dynamic braking or rheostatic braking. And the motor speed cannot become negative with dynamic braking. Can it become negative? Yes. With dynamic braking, can the motor speed be negative?
No, sir.
No, sir.
Yes, anyone?
Means motor
sir.
is moving in opposite direction.
Is it possible with dynamic braking?
No, sir. Rheostatic braking, no.
Pakka?
Yes, sir.
Yes, sir. Yes.
Yeah, 100%.
Yes, so yes, sir. We actually remove the supply and we connect the means external resistance with our armature. Means so. Negative speed is not there.
Now I will say that it is possible. How? I'm saying that
So
you
when
can
the
have,
greater than
yes. In case you have an active load which is able to drive the motor in the opposite direction. Okay? Then in that case, negative speed is also possible even with dynamic braking.
yes, sir.
Okay. So if you have a passive load, this is the characteristic up to point B. But if the load is active, you can go beyond this also. Okay. Okay. If we similarly find out the equation for current, this is the equation for current. Okay. You can draw the graphs. You will see once again that as soon as you initiate dynamic braking, and if you neglect the armature inductance, you'll find that the current, armature current, will reverse instantly. Correct? As soon as you disconnect the supply, and connect an armature resistance, external resistance in the armature circuit, and if you are neglecting the armature inductance, what happens to the armature current? It reverses instantly. Okay? So this is the equation for the armature current. Okay? This I in is the initial current. Can anyone tell me what is the value of this I in? What is the value of this I in?
K5 omega N by R.
Yes, it is K phi omega or C omega upon R. But it is simply the back EMF divided by the armature circuit resistance. Okay? And armature circuit resistance includes the armature resistance and the braking resistance. Okay? As the speed decreases, your back EMF also decreases and your armature current will also go on decreasing exponentially. ठीक है तो I'm stopping here.